Welcome to the third part of module 4 stereochemistry, that is geometrical isomerism. So in this presentation we will be discussing about stereoisomers and its classification, and then we will be looking into geometrical isomers. So we move on to stereoisomers. Stereoisomers can be classified into two categories. One is configurational isomers and the other one is conformational isomers. Configurational and conformational, these two words are very important. Configurational isomers means they have different spatial arrangement. The arrangement of the different functional groups in space is different. Whereas conformational isomers means they have different spatial arrangement due to free rotation. So free rotation is possible around the carbon-carbon bond. We will be seeing that in detail later. Configurational isomers can be separated into the different individual isomers, but conformational isomers, they cannot be separated. So we will start with configurational isomers. Again are classified into two categories, namely geometrical isomers and optical isomers. Now let us see what are geometrical and optical isomers. Geometrical isomer means it is shown by compounds having restriction to free rotation. What is this restriction to free rotation? Now if you look at this animation, you can see, so this is an olefin, a compound containing a double bond. This is carbon, so you have a carbon-carbon double bond, and you know very well that double bonds are stronger than single bonds, and so these functional groups, they cannot freely rotate about this carbon. So that is what is meant by restriction to free rotation. The geometrical isomers, they show restriction to, or compounds showing restriction to free rotation, they generally show geometrical isomers. Another name for geometrical isomers is cis-trans isomers. Coming to optical isomers means these are compounds which can rotate plane polarized light. Now what do you mean by plane polarized light? You can look at this figure. So light, it has vibrations in all directions. You can see that the red one, that is in the x-axis, the blue one, that is in the y-axis, and the green one, that is in the z-axis. So when light passes through certain materials like nickel prism, the vibrations in one direction only will be coming out, and that type of light is called polarized light or plane polarized light. It is polarized, or the vibrations are restricted into a single plane. So optical isomers, they can rotate this plane polarized light in by some angle. Actually it is by some angle, and such isomers, they are called optically active isomers. So cis-trans isomers and optically active isomers, these are the two classifications of configurational isomers. Now let us on to geometrical isomers. Geometrical isomers, I told you it is cis-trans isomers. So cis means adjacent, the same side. Trans means opposite. So cis-trans isomerism. If you look at this example, 2-butene, so you can see it's an olefin. It contains a double bond. So there is a double bond at the center, carbon-carbon double bond, and this carbon has two functional groups attached. One is the methyl group and the hydrogen, and this carbon also has a methyl group and a hydrogen attached. So this compound does not allow free rotation about the carbon-carbon double bond, and due to this we can get two spatial arrangements. These two spatial arrangements are fixed arrangements. So you can see this example. These are the two spatial arrangements. This one is called cis and this one is called trans. So here, if you look at this compound, these two similar groups, methyl groups, they are on the same side, adjacent. They are on the same side of the double bond, and so that is called cis. Whereas here, if you look at these two methyl groups, they are on opposite sides, and so they are called as trans. So if similar groups are on the same side of the carbon-carbon double bond, that is known as the cis isomer, and if similar groups are on opposite side of the carbon-carbon double bond, that is called trans isomer. It's a very simple thing. You might have learned this in your lower classes also. Cis and trans isomers, that is adjacent and opposite. Cyclic compounds also show this type of isomerism. Okay, let us see some examples. Two important examples are 1,2-dimethyl cyclobutane and 1,2-dimethyl cyclohexane. So you can see this is cyclobutane, and these are the two adjacent positions 1 and 2, and this is cyclohexane 1 and 2. So 1,2-dimethyl, these are the compounds. Now this compound 1,2-dimethyl cyclobutane, that shows cis-trans isomerism. How it shows that? We can see that this is the cis form and this is the trans form. So you can see here the methyl groups are projecting in the same direction, that is called cis isomer. Similar groups on same side of the ring, that is cis isomer, and here similar groups are on opposite sides of the ring. So this is projecting to this side, this is projecting to the opposite side, so that is the trans isomer. So in cyclic compounds, similar groups, if they are projecting to the same side of the ring, that is a cis isomer, and if they project on opposite sides of the ring, that is trans isomer. Similarly, you have cyclohexane, 1,2-dimethyl cyclohexane. These are the cis and the trans forms. So you can see in the cis form, similar groups are on the same side of the ring, and in the trans form, the similar groups are on opposite sides of the ring. So this is cis-trans isomerism. Cis-trans isomerism is shown by olefinic compounds, and it can also be shown by cyclic compounds. If you take this example, this is an olefinic compound. Let us see what type of isomerism is shown in this compound. So it is not possible to say whether this is a cis isomer or the trans isomer. Why? Because all the four groups are different. Okay, suppose this OH group is on this side and this COH is on this side. We cannot differentiate between this compound and the other compound. So the terms cis and trans are meaningless if all the four groups around the carbon-carbon double bond are different. That is the situation here. All the four functional groups are different, so we cannot distinguish which is cis and which is trans, or cis and trans, the words are meaningless. That is adjacent and opposite, the words are meaningless. So in this case, what will we do to differentiate between such type of isomers? So we have to follow a different type of naming, and that is called the EZ nomenclature, EZ system of naming. Now E stands for antigen, which means opposite, and Z stands for zusammen, which means together. These are German words. So E means opposite and Z means together. Now how do we designate which is opposite and which is together? For that, the groups around the carbon-carbon double bond have to be assigned priorities. One has more priority, the other has lesser priority. So once the priorities are assigned, we can designate them as E, that is opposite, or EZ, that is together. Now if you look at this compound, these two groups, OH group and COOH group, that is on one side of the double bond. The other two groups are on the other side of the double bond. So out of these two, OH and COOH, which is prior or which has more priority? So we have to assign priority to these groups. Similarly, CH3 and CHO, we have to assign priority, which has more priority, that we have to assign. And these priorities are assigned on the basis of certain rules. So there are three important rules for assigning priority. Let us see those rules one by one. The first rule is like this: the atomic number of the atoms directly connected to the carbon, that is important. The atomic number of the atoms directly connected to the carbon are considered, and priority is assigned in the descending order of atomic number. That is, greater the atomic number, higher will be priority. So the carbon of the double bond has two groups attached to it. So in these two groups, some atom is directly connected to this carbon. The atomic numbers of these atoms are taken, and greater the atomic number, higher will be the priority. For example, let us consider the same compound here. So let us see OH and COOH, these two functional groups, they are attached to this carbon. But in the OH, the oxygen is attached to this carbon. Here, this carbon of the carboxylic acid group is attached to this carbon. So the oxygen has atomic number 8, carbon has atomic number 6. So higher the atomic number, more will be priority. So oxygen has more priority compared to carbon. So this OH group is given priority 1, and COOH group, that is given priority 2. So in this side of the carbon, you have this OH group first priority, and this COOH group second priority. What about these two groups, CH3 and CHO? Now if you look at these groups, the carbons of these groups are connected to this carbon. Okay, and carbon has atomic number 6. So here we cannot distinguish on the basis of atomic number. Both are the same element. So in that case, what will we do? In that case, we have to follow the second and the third rules. So what is the second rule? If the atoms directly attached to the carbon are same, that was the earlier case, CH3 and CHO group, then the atomic numbers of the second atoms are considered. Okay, and if they are also same, the third atoms are considered, and so on. So that is the second rule. If the atoms directly attached to the carbon are the same, then the atomic numbers of the preceding atom, second, third, etc. will be considered, and we will assign priority. And the third rule is multiple bonds are taken as separate single bonds. If you have multiple bonds like C double bond O, if you are having, that is considered as two separate single bonds. Okay, now let us apply these rules. So you have here carbon, these two are carbon, and so the first atoms attached to this carbon, they are the same, and so look at the second atom. Second atom here, 3 hydrogens. Okay, but here you have 1 hydrogen and 1 double bond oxygen. So double bond is considered as separate single bonds. So in this functional group, you have 2 oxygens and 1 hydrogen. Whereas here you have 3 hydrogens. Okay, so let us take the total atomic number. That will be easy. Here total atomic number is 3. Here total atomic number 2 oxygen means 16 plus 1 hydrogen, 17 is the total atomic number. So this group, that is the CHO group, has priority 1, and CH3 group has priority 2. So now we have assigned priorities to the functional groups on both sides of the double bond. Now what is the next step? The next step is very simple. If both groups of higher priority are on the same side, the isomer is designated as Z together. Whereas if the groups are on opposite side, the isomer is designated as E. That is antigen, opposite. Okay, let us look at this example. So you have the priorities here. Now you see priority 1, the two groups with priority 1, they are on opposite sides. So we can designate this compound as E. So this is E. Okay. Now let us look at some more examples, then the thing will be more clear. Let us look at this example. Now in this compound, you have these groups OH and COOH. They are connected together. So O oxygen is has greater atomic number than carbon. So first priority for OH, second priority for COH. Here again CH3 and H. So carbon and hydrogen. Carbon has more atomic number. So this has more priority compared to this one. So priority 1, priority 2. Now look at the priority 1. Priority 1s on both sides are adjacent, are on the same side. So this is EZ together. Okay. Now third example. Now this is a little bit complicated example because you have some larger functional groups here. So on this side you have C3H7 and on this side you have C2H5. You have to assign priority which has higher priority. So first you have the first atoms connected are carbon, then you have to look at the second atoms and then you have to look at the third atoms. So rather than that, there is an easier method in case of alkyl groups alone. In case of alkyl groups, higher the alkyl group, more will be the priority. So C3H7, that is a larger group compared to C2H5. So the priority will be more. So C3H7 has first priority, C2H5 has second priority. Even the other way around you can do. You can check the first carbon, then you can go to the second atoms, then you check the third atoms. You will get the same result. But this is little more easier when it comes to alkyl groups only, not applicable to other functional groups. Alkyl groups only. Larger the alkyl group, more will be the priority. So C3H7 has greater priority than C2H5. Coming to the top portion, it is CH3 and H. So definitely CH3 will have first priority, H will have second priority. Now you can see the higher priority, first priority groups are on the same side and so it is Z, Zusammen together. Last example, again this compound. So at the bottom portion it is OH and COOH. Priorities, OH has more priority, COOH has second priority, and here in the top portion you have NH2, nitrogen and carbon. Nitrogen has more atomic number compared to carbon, so NH2 group will have priority 1 and CH3 group will have priority 2. So you can see here the groups with same priority, they are opposite side, and this is E. Okay, so this is the EZ system of nomenclature or EZ system of naming for geometrical isomers.